Um, Hello, everyone. Nice to meet everyone here, and welcome to join our session. My name is Chongyu, and together with me is Nick, my teammate. So we are from Grab, AI and experimentation platform team. So today we are going to share our journey in building our own user-centric foundation models at Grab and how Ray is used in our work. So first, quick introduction of our Grab. So we are a super app based in Singapore, and we started in 2012, operating in one city, and today we already operating in 8 countries across 800 cities. So we started as a ride-hailing company, but now we have expanded our business into multiple verticals, including food delivery, grocery shopping, logistics, advertisement, and more. And also at the core of a Grab ecosystem, we also provide digital wallet and lending solutions, which enables the seamless transactions across all the services we provide in Grab. And as a platform teams, over the years, we have created a lot of data from our users and our customers. Those data are essential for us to design customized experiences to our users and for us to continuously improve our offerings to our users. So here are just some examples. First of all, we have user transaction data, which cover all transactions across all of our verticals. This gives us a comprehensive picture of our user purchasing patterns. Then we also have user click event data that basically summarize how users interact with our app, which will help us to make our app more intuitive and provide a more customized user experience. Then on top of that, we also gather preference data from both our users and drivers. They can specify their preference, their preferred pickup and drop-off locations, then for us to understand them better and provide individual experience to each one of them. We also, for our merchants and drivers, we will also provide inside data based on their sales history. So that will help them to grow their business and in a more smarter and more effective way. On top of that, we also have our marketplace data that includes the supply and demand, traffic conditions, or even weather at any given location and given time. So those data are also very crucial for us to better plan our marketplace and offer more efficient decisions in our marketplace. Then last but not least, as an experimentation platform, we have all the data from all of our experiments across all different services. That includes our user responses to our new features and also the impact of different treatments as well as a network effect to our marketplace. With such a diverse and rich data, that gives us a good opportunity to truly understand our users and also help us to design and keep improving our services to offer our users. Traditionally, how this data are used in Grab, basically we have 3 approaches. It can be manually created attributes, which we have user analysis team that analyze the behavior of users, then summarize their unique characteristics into user attributes. We also have some teams building specialized models to learn the representations from the data tailored to each individual use case. Some teams also build knowledge graphs to indicate the connections between different pieces of information, which can provide a structured way of the relationships within the data. But then in recent years, we keep asking ourselves one question: can we do something a little bit unconventional. Instead of continuing improving our user attributes, specialized models, can we build a foundation model that learn from the data directly, then which can be used in our different downstream tasks? This is how basically we started this work. So our goal are in twofold. From training the foundation models, our first goal is to extract the embeddings for all the entities in our marketplace. That means the users, drivers, merchants, as well as our marketplace. Then those embeddings can be used in different kind of downstream tasks. The second goal for this work is to provide the foundation models to be consumed directly by downstream tasks. For example, downstream tasks, they can take the foundation model and fine-tune based on the use case-based data that can help them to solve the data sparsity and co-star problem. We are in the first phase of our work, so we are focusing on the embedding use cases right now, but we have made some good progress in the past year. So we have onboarded several different use cases from different verticals, and from our current exploration, the results are quite promising. We have seen improvements in those tasks compared to traditional methods or specialized models. Yeah, so now is a fun part, basically how we build the model. I'll hand over to Nick to discuss how we build the model and how Ray is used in our work.
Okay, thanks, Chongyu. So I'm going to talk about how we build our model. And maybe the first question is like, why didn't you just fine-tune an LLM? And this talk is titled like user-centric foundation models. So LLMs are great at general tasks, but they really lack about knowledge about our users, about our merchants, drivers, what are the locations, everything that is very essential to our enterprise. And this motivated us to build our own foundation model. So there are like several challenges, like for example, we start with the tokenization. How do you define the language of the users? How do you capture user attributes, user interactions? The second part then comes like once you can model this, how do you design your ML architecture that can understand your user data? And the last part, I guess that's also why we are invited today, is like about experimentation. So first we need a framework that allows us to train on billions of multimodal tokens distributed over multiple nodes. And what sometimes gets overlooked is that it's also very important for a framework that supports quick experimentation, because if you build your own model, things usually don't work on the first iteration. So the faster you can iterate, the more likely you're to succeed. So let's start with the first topic, the tokenization. And one of the key drivers of user understanding are user attributes, aka tabular data. They capture more long-term behaviors. So for example, we have like the dietary preferences, user age, how they pay, where they live, and etc. Another source of important information is the time series behaviors, so sequence data. For example, we have National Day. So this is the date, then certain user receives an ad that motivates him to search for merchants. He orders pizza, he drives, gets a ride to somewhere. So how do we learn from both this tabular and this time series data? And one of the first things we really tried is like a vanilla tokenization. So we see a certain cell in the table, which consists of the column name and the value as a token. And similarly for time series data, there's like the date, which gives the type of the action, and then the value, which is, for example, National Day, or the type of the action is order merchant, and then the merchant that is ordered from is ID 45. So what you can do in a very vanilla fashion is you just say this is a certain ID. Then you can cast that to an embedding layer, look up the embedding, train a standard language model. But you have kind of two issues. The first is your exploding vocabulary, because now each unique token is like one ID, and your vocabulary just becomes very huge. The second problem is that you're not really using some of the information. So for example, you have order merchant ID 45 and then view merchant ID 45. So you ideally should share some information that this is the same merchant, which is not guaranteed with this tokenization method. So what can we do better to solve this? And the first innovation is to see tokens as a key value pair, where the key kind of gives the context of the event and the value is the value of the event. And the nice thing about this is that it's generalized both to tabular data, so you have like the column name value combination, as well for time series data, you have the action event, which is like the order merchant, and then also the value of the two. But you still have one remaining problem, which is that still your vocabulary explodes. What can you do about that? And for this, we changed the perspective. So instead of seeing things as individual like IDs, we see things as modalities. So for example, all of the keys you can see as a text modality. Similarly, for categorical values like dietary preference, vegetarian, this is also text. We see numerical as a different modality because LLMs are not too strong, getting better, but still not too strong on numerical data. And then we also have other things like merchant IDs, locations, and etc. So what do we do with this new view of the modalities? We design adapters. So for each of these modalities, we have a specific adapters. For some, we leverage pre-trained foundation models. For others, we do custom designs. And the beauty of that, it really allows us, if we have new data types at Grabs, we can introduce a new adapter, learn from that, and then extend the capability of our foundation model. So to give a bit more context, I want to get into an example of our merchant adapter. So here we have order merchant ID 45. This adapter consists of a pre-trained text embedding model that takes the key, the order merchant, to get a representation and combines it then with the embedding of an embedding layer. So at this point, it doesn't seem like a big innovation. It's like, okay, still an ID for an embedding layer. So why are we so big about the adapters? And I think it's really about the spirit of adapters. Adapters are a replaceable component. And for example, one thing we're currently working on is like the merchant adapter V1. So going beyond the single embedding layer, but also like capturing other attributes, like what items does a merchant have, what are the opening hours, where are the locations. And this really helps with the cold start problem because for a single merchant, maybe you don't have an embedding ready, but you have all these attributes, so you can already start learning from that. So now we can understand the different modalities, but how do we build a foundation model on top of that? So I want to talk about 4 points. So how do we jointly learn from tabular and time series data? Both have very different requirements. Tabular data needs to be column invariant, so you don't want to have different predictions if you change column order, whereas for time series, the order of the actions is very important. The second question is, how do we train a model? How do we design a pre-training objective? Third, we have a lot of merchants, we have a lot of locations, drivers, and etc., which results in huge vocabularies. So how do we deal with those? And lastly, how do we generate embeddings out of the model that can then be used in downstream use cases? So let's get started with the model design. So at the bottom, we both have the tabular data and the time series data, and we want to input both. And as mentioned before, we want to keep column order invariance, and also we want to learn for time series data. And to kind of keep both properties, we use learnable tokens for tabular data and have more standard position embeddings for both absolute and relative time in our model. The next question then becomes, we can understand the data, we can feed it through our adapters, we can feed it through the transformer model, but how do we learn about Grabs data? And one of the initial tries we had was to take a supervised task, we do supervised fine-tuning on a large scale, and then in the end we would extract embeddings. But we found that especially for a Grab app that's so diverse, you can book a ride, you can book food, you can do grocery shoppings, you can even open a bank account. Like a single task is biasing the embeddings towards a certain thing. So we found that the solution is actually to pre-train, to avoid biasing the model towards a task. And what we do for that is like we use a combination of masked language modeling and next token prediction. So we have certain masked tokens, we reconstruct them, and then because our input data is multimodal, we also need to design different heads for different modalities. And for example, for the user IDs, they can be either a classification or similarity losses. For numerical, something like a mean squared error loss. So are we done yet? Is this easy to train? And no, it's not. We have one of the challenges. So if you see in the user ID adapter, there are the embeddings. And we have a lot of users, around 40 million users monthly. So if we want to pre-train only on a monthly scale, our embedding layer is already 40 million parameters. And just for a comparison of a similar sized model, we have here a Qwen 3, which has a vocabulary of 150K tokens, embedding them of 2048, and the memory footprint on the optimizer is very minimal. At the same time, if you want to put our embedding layer on the GPU, that's already hundreds gigabytes of GPU used. And we're not like a big company like Meta where we have an abundance of hundreds H100s. So 100 gigabytes of GPU memory is like very, very valuable to us. So what can we do to solve this? And we do two things. The first realization is that in a batch, usually not all the embeddings in the whole embedding layer are used. So we can use a sparse atom optimizer that kind of approximates the full atom, and that helps us to reuse the memory. The second thing then we can do is, because we don't have that many IDs actually in a single batch, that we not necessarily need a GPU, but we can offload the embedding layer and the state of the optimizer to CPU, so completely freeing the GPU from the embedding layer and having the full capacity to train our main model. Are we done yet? No, because we do pre-training. So we also need to, for example, characterize the next merchant a user would order from. And if you were to employ like a vanilla classification layer, similar to what you do in LLMs, then again, like your computation flops are huge because your like classification layer is huge, and then also like the size on your optimizers is very huge again. So the first iteration, we had like the hierarchical classification. So your classification network is still very big. Maybe for context, what you do in hierarchical classification is that maybe for a merchant, you first classify the city, then location, and so only a sub-network is already active for a single sample. So you significantly reduce the flops, but still memory requirement is very high. And then the second iteration is then that we use a BYOL style target network that we update via exponential moving average. And this allows us to both reduce the size of the target network and also the flops significantly. And again, we can offload everything to the CPU to even free more GPU memory. Okay, so now we can train a model, but how do we extract value? And as highlighted earlier, like one of the easy things is to fine tune, but maybe a less invasive approach for our downstream users is to use embeddings. So we can extract general user knowledge from our foundation model and then provide it to our downstream use cases so they would consume embeddings as additional features. And we have two types of embeddings. So first are the long-term user embeddings that come out of our ID layers. And throughout training over historical data, the model sees a lot of the behavior of the user and kind of learns long-term patterns of that user. The other important thing are like the short-term user interactions. So for this, we construct the most recent time series, we put it through the model, and then we do some sequence aggregation to then get a short-term user embedding. And as showed before, this works very well for a lot of tasks. It seems to generalize well, but was it always that case? And actually, if we look at the improvement curve, like in the beginning, it was not really working well. And we did a lot of iteration cycles on like data set creation, so finding out which events are important, like how do we avoid duplicates, how do we represent the data, how can we, for example, for location, how can we represent it, how do our adapters get it. Then on the model design, like data representation and adapter design are closely tied together. How do we deal with the different head designs, like I showed, hierarchical classification, target network, time encoding, also very important, main transformer design, and etc. So continuously iterating to get better and better over time is very important. So yeah, machine learning is actually all about experimentation. So the more you can iterate, the more likely you're actually to strike a good result. And to get there are two things that are important. And more classical, what people look at is the training time. Of course, the faster you can train, the more likely you get good results. But the second part is not only training matters, like it also matters how fast you can implement your things to again try them out. And in both areas we were previously lacking. So before Ray, like we needed to go through multiple cycles of iterations. So how usually that was running was like you need to create a Spark job, you need to define your pre-processing logic, you need to decide like how big is the data you want to do your experiment over. Like if you choose a large scale, then maybe your pre-processing job takes forever. If you take a small scale, if it works again, then maybe you don't know how well does it scale to a lot of data. At the same time, you also always need to manage your storage path, like know what data set did what, like what experimentations did you do. So like a lot of manual work. At the same time, on the training side, we were only supporting single node training. So if you want to go bigger with your model, you can only scale vertically, so a bit limited. So iteration cycles were just very, very slow. But we also had another problem. So the training itself was also very slow. To generate embeddings for 1 million users, it took 10 hours to pre-train. So not really scalable for all the users we have. And one of the reasons was the slow GPU utilization. So we only had around 19%, which is very poor. So we dove then into why is this happening. And the reason for that is the fighting for CPU resources. As I said previously, we don't have that many GPU resources, or like not that many as big companies, so we offloaded a lot of the CPU. But now a lot of optimizations are on the CPU, so now our training becomes CPU heavy. At the same time, we're experimenting a lot with like data filtering, how do we represent data. So also our data loader is kind of expensive with the last mile data processing. So data loading is also CPU intensive. And now if you have both model training and data loading on the same node, everything is fighting for limited CPU resources. And I think this is like a very much overused race story. So what do? You have a heterogeneous cluster, like you scale your CPUs, you scale your GPUs, and then you're in a happy state. And that's actually also what happened for us. So we decreased training time by 6x. We have a heterogeneous cluster where you can do last mile data preprocessing, and overall the GPU utilization went up to 85%. You might still say like, hey, why are we not close to 100? I think this is not feasible right now because we still have a lot of optimizations on the CPU. So I think 85 is like a very good place for us already. Okay. So I think, yeah, it was a bit fast. We have a lot of time for questions. But basically, this is our summary. So the user behavior on our Grab app is very diverse. It spans across multiple aspects of daily life, which at the same time provides a great opportunity for us to learn a more holistic understanding of our users. The difficulty of this variety is that the data is quite multimodal. We have like text, categorical, locations. We constantly add new adapters kind of to cater more use cases. So with adapter-centric design, this enables us to be kind of more future-proof. We showed how we can pre-train our model and extract embeddings. And one of the important things is like if you build such a model from scratch, then you need a lot of experimentation to make it work. If you want some more detail, we actually have a blog post, so you can check that one out. You can type that thing in, or if you have access to the slides, you can just click on the link. So the question is kind of what is next there? And the typical story of foundation model is like always scale, and we've also seen good experiments with like both scaling the model and the data. Another big area is the pre-training objective itself. So as I highlighted before, we do like mass language modeling and next token prediction, which usually only cares about a single token. But for embeddings, we not care about a single action. We want to summarize the whole user journey. So there is kind of a mismatch between what we pre-train for and how we use things. So we're like researching on better pre-training objectives that kind of bridge that gap. Another thing is like what I showed with the merchant adapter V2, where you take the items, location, etc. So for events, taking in multiple parameters. And then also a big thing is like inhomogeneous time series encoding, because like events are not happening with fixed time spans in between. Like users can take days in between, they take other actions, other things are happening within seconds. So this is also a problem we like addressing. Yeah, I think that's it from my side. Thanks for listening, and we're opening for the Q&A now.
Yeah, thank you so much for the talk. So if you have any questions, please raise your hand and I'll bring the mic to you.
Hi, great presentation. I'm just curious, could you talk about how do you make sure the embeddings that are finally generated like make sense? Like how were they like evaluated? And secondly, could you talk about even what kind of, like you talked about relative time while generating the, for time series data. Curious what kind of positional embeddings were used there as well? Like, yeah.
Okay, I think the first thing I can definitely answer. So one of the important things is like we need to closely work with our downstream users. So usually what we do is like we onboard their model to like a set of embedding benchmarks, and then we can measure the performance that such an uplift would give. So this is not interpretable necessarily, but you can justify like just by using the embeddings, you improve the user understanding and resulting in a higher AUC, for example. But we're also working on more explainability analysis, kind of finding out what is inside the embedding. Yeah. But usually the justification for our users is like, if it works better, then they're very happy. On the second part, I think this is a bit confidential, so I cannot share too much. Sorry.
Any more questions?
So two parts. First, I wonder if this foundation model is used for recommendations now, and if so, how it compares to any sort of legacy recommendation models you used.
Okay, I think, so for our team, if teams still want to use the traditional recommendation models, they can still use our embedding as additional input. What we're currently exploring is like, if teams are willing like to replace their whole architecture with our model, because the future we think is in time series learning. It's not in the wide and deep architectures. So yeah, there's also some exploration going on like to replace the whole model.
Any? Oh.
Hey, great presentation. Do you guys train on like web data too? Like, does the foundation model you train have any like general knowledge from the internet, or is it just grab data?
Yeah, so I can probably take this. So majority of our training data, grab data. So because we want to learn the grab context and the data which is only reasonable for grab business. We want to learn the context of that. But we do use the public available text embeddings to help us encode some of the context, like the descriptions and the cuisine tab. This is kind of like a common knowledge that everyone understands. So on that part, we do use public available. Yeah.
Yep. Any other question?
Have you seen any benchmarks on if you were to apply the same architecture with a classification head or some regression head on top? How does the performance change if you use, like general, self-supervised embeddings versus actually tune it on a particular task? Does one do better than the other?
Yeah. I want to take on that. Yeah.
Yeah, we're experimenting. Like, so the main focus has been on the embedding use case because it's less invasive. Like, people like their models. Usually, if you tell them, like, let's replace your model, they're not so happy. We have tasks where we've seen that pre-training can help if you fine-tune on top. But for some tasks, it's challenging to transfer the knowledge to the fine-tuned model. So it's not always working right now.
Thanks.
So for the text embeddings, it seems like you guys are using standard, like Word2Vec or Glove or something of that sort. But then do you backpropagate to the text embedding layer as well? And then, so that way you have embeddings that are fine-tuned for your particular use case? Or you leave the text embeddings the way they are?
I'm not sure whether I can.
Yeah, right now they're like frozen foundation models, so there is no backpropagation right now.
Okay, thank you.
You mentioned about the experiments where you guys didn't see any results and then you started to see improvements. Can you just talk a little bit more in terms of like what were your learnings from your first experiment to something that you see today?
Yeah, I think the biggest jump is probably V0 to V1. So this was like an iteration of how we extracted embeddings, because not necessarily everything is like meaningful you can extract from the model. So this is like the biggest leverage that came. And then other things are like small, or that not potentially changes, but you realize that certain parts of the model, how you pre-train, that are not optimal, like losses are not necessarily converging. And then you can make assumptions what is happening and then iterating. And then of course of the data, you can feel like, okay, this certain task, if we onboard something, we don't capture these kind of events. So it's very, like surprising it even works, but if you add new events, like you can get more general embeddings.
Thank you.
Yeah, so we almost at time. So last question. Yeah.
You know, for these foundation models, are they used for recommendation services to users, or do PMs like Grab use it to build new services?
Okay, so mostly data scientists are using them right now.
Yeah. Thank you so much. And yeah, please give a round of applause for Nick and Chongyu from Grab.